Hello everyone. I'll start in like 5 minutes. Right. Select 205. If there's any particular topic you want me to go through in detail, you can message the chat and I'll make sure to put more focus in that area. Oh yeah, do let me know if there's any mic problems. Right, just in case. Well, I guess I'll start right on now then. Right, so let's see, just get the slides up. Should be up now. And should be able to see it. Alright, so welcome everyone to the second half of MATH2901. This part of the course is about statistical inference. Oh, whoops, that's not straight. And credits to Rory for his slides, right? It's mostly his, but I added some things just to make it more 2901. Right. And as you can see, it's mostly statistical inference. And the concept is, well, we have data and we want to build models off it. Right, build models off it, so we need to estimate parameters. So in a sense, it's kind of the reverse of the first half of the course. Right, first half you assume the distribution and then you found some properties. Here we more so look at what the properties of the data is, like inherently, and then we fit it to a particular data set or model, and then we estimate the parameters. Right, so I'll just go through this. Right, so we'll firstly need to find what's a sample. Right, sample is really simple. It's just the concept of having a bunch of ID observations. Right, size n doesn't really matter. Right, you just have a set of observations. So it could be, say, weight of population. Right, you just select a bunch of random people from, say, New South Wales, and that could be your sample about the distribution of the weight of people in New South Wales. Right, and lowercase again is observed data, and uppercase is it means it's random. Whenever we work with statistics, we assume we have random data essentially, right? Because realistically speaking, we have the data that we collect, so like 50, 25, so forth, so actual numbers. But when we build up our like models and estimators, we assume it's all theoretical, so it's more general in nature, right? So we have this term called statistics. A statistic is just a function of the sample, right? So for example, this is a statistic because it's a function of the random variables. As you can see, it's all in terms of the random variables. Same thing with the sample variance and the sample median. Right, these are all things you probably saw before, right? Just common statistics you would see. So we'll focus on the sample mean because that's the easiest one for now. And we have this theorem about it. So as long as you have an IID random sample with mean mu and variance sigma squared, you have these two results. This is probably something you've seen a lot of. It probably reminds you of CLT in a sense. Right, similar, or I should say reminds of CLT. And you can easily kind of show the variance is this by just using properties of variance and independence, right? You can bring this factor out, square it, and then use independence over here so that there's no covariance between the two. And then you notice that they're ID, so same variance, and thus you have n times the same variance, and so you have this, right? So this should be relatively straightforward, so kind of skip that now. Now we move on to estimators. So an estimator really is just a statistic. It's just a function of the random variables that you observe or collect, right? And the whole idea of estimator is that since we collect data, we assume it's from some sort of distribution, we have to figure out what this is. Have to figure out. You have to figure out. Oops. And the way there's an infinite number, so we're going to kind of narrow our focus to particular estimators, right? Obviously, we want useful estimators. And the way we will define it in this course is by looking at the mean square error. So mean square error, right? And the lower it is, the better, right? So how it forms an average. The idea is similar to least squares. But before we look at it in particular, we're going to look at two other values or figures. The first one's going to be the bias. So the idea of the bias is that you just look at a point figure and you see on average how far off it is from the value you're trying to estimate. Right, so this is the mean value of estimator, right? Of estimator. And you want to see how far off it is. Okay. And this is true value. Right, you want to see how far off it is on average, right? And obviously if it's, well, the same thing on average, so 0, the bias is 0, it's called unbiased. Right, now if we can go for an example of this, right, since it's really just expectations, it's not too complicated, assuming the random estimator is also fairly simple. So if you look here, it's kind of a weird kind of average thing, but it's not too difficult to calculate because it's all linear in nature, right? As you can see, it's linear with respect to the x1s and the x7s. Right, here they're Poisson, so you'll note they have the same mean. Right, so we go with this. We find the expectation. We just use the fact that expectations are linear and bring out the constant term and just split it out individually. And then from here, we just note that they all come from the same distribution. Xi, R, I, D. So they have the same mean. So you just go lambda, so 2 lambda here, and 7 lambda here. So lambda. You add them all up, and you'll see this. Right? And then when you calculate the bias, you can see that for this particular estimator, it's actually unbiased. So that's pretty good, right? On average, it doesn't deviate away from the true value if you were to average all your values. Right? But since this is only a point estimate, it's insufficient because, well, you're dealing with a random variable, right? This is random. So we need to consider variability. Right, random, so you need to consider some sort of random variability, and that's what this part is, the standard error, right? It's really just standard deviation, so standard deviation. Well, we just call it error because in our context, our estimator is what we're trying to figure out the true value of the parameter, and so there's got to be some error involved in our estimate. So that's why this is the error word here. Right, so you just square root the variance. And here you just use the fact that, well, you know how to deal with variances. Right, so we just kind of go with this. In this case, we'll offer the same example from before. We bring out the constant term and square it. And then you note that they're independent from one another, so you can just add the variances. And then you just combine everything by noting their IID. So this, and this are all the same. And since xi is Poisson lambda, that means variance of xi equals to lambda. Poisson. And you just kind of combine things, and eventually you'll see this is the answer. Right, and hence the standard error, which is just the square root of the variance, is just this. Right, that's fine so far. But the only issue with this, right, yeah, sure, we found the standard error, is that if you look closely, this thing here is a true parameter that we're trying to estimate, that we are interested in. Right, so we don't know its actual value. So it's kind of hard to say what this figure is because you're trying to estimate lambda in the first place, right? So since our standard error depends on lambda, it's kind of like, okay, what do we do? So the way we can get an actual figure right now, naively, all we do is, well, we estimate that. And the way we do it is we just plug in our estimator value. right? It's probably something you would have just thought of on the spot, like, okay, how would we do this? Okay, we just plug the number in, right? And it turns out, asymptotically, within this course, because we're dealing with MLEs and stuff, this actually works out really well, right? And as you can see, we'll be doing this a lot in this course, right? So whenever you don't know a specific value in the standard error, right, if it's unknown, you just kind of plug it in, and it usually works. Right, so for this example, so we go back to the previous example, so same estimate and everything, we know this is a theoretical standard error. So our estimated standard error, well, we just plug in lambda hat, plugged in, right? And this is something we could actually find as a value because it's based on our random sample that we collected. And so we can actually evaluate this as a figure. Right, that should be it. And notice how there's a hat on top of the SE, right? Because that means the standard error itself is estimated. Now, the whole reason why we kind of went through those two concepts of bias and standard error is because they kind of combine into this one statistic, or not statistic, one figure, right? And it's called the mean square error, right? And the way it works is that it kind of measures how far off our estimator is from the true value. Right? So it's kind of, well, mean square error, right? You want to see how far off on average the squared error is. So you find the expected value of the square error, right? And it turns out you can break it down to these two things, bias squared and variance. Right, so this is probably something you've seen a lot of, but I imagine you've seen a lot of, but it's something you also probably need to know how to prove. Right, so if we look at the definition of the mean square error and compare it to like the right hand side, you can see there's a variance term here. And if you recall, the variance of an estimator, I'll just do variance of x is equal to the second moment minus the first moment, second moment around the first moment. Right? You know it's in this form. And then if you look at this is sigma hat. So you need to introduce a minus the expected value of sigma hat in there somehow. Because if you do, or you plus minus it, right, you'll eventually get this thing. Right, so that's what we're going to do in the first place. Right, and that's what they do in the proof here. Right, we plus and minus the thing we need. Right, standard technique in mathematics. Right, and then we kind of just perfect square it, so you end up with 3 terms. Right, perfect square, you get 3 terms. And then if you look at the first one, this is just the variance, because this is variance, or sigma hat. If we look at the second term, if you look closely at the second term, this thing here, this is a constant, so is it, and the expected value of a random variable is also a constant, right? Both constant. And so the squared of a constant is also a constant, so you can just take it out, which is what this whole thing is, right? Well, that should be squared. Anyway, yeah. So you see this thing, right? Constant squared. Well, constant squared is still constant. You can bring it out, right? So we have the bias squared, or sigma hat, sigma. Oh, theta, whoops. Right? So we have the two components now, right? We have this and this, this and this. So you just need to show that this remaining part over here is actually equal to 0. Right? If you do, you're good. So just focus on that part now. If you recall earlier, like so over here, this thing, the first part was random. The second one was constant. And since we're dealing with a perfect square, you're going to multiply the 2 in the second term because you get like x plus y all squared equals x squared plus y squared plus 2xy, right? So there's going to be a constant version. So 1 over the half is going to be a constant, this thing, right? Look at this is constant from our previous observation. So we can bring it out. This is what happens here. And the only random part now is this thing. But if you look at it closely from here, this itself is a constant. So you can bring it out of the expectation. So you get this. So you just end up with expected value of x minus, or sigma hat minus a constant. But these two things are actually the same. So it turns out to be 0. So this red thing is 0. Right. And as you see, this relies on you knowing the properties of expected values. Right? You can take out constants and how, yeah, pretty much just depends on how well you know expected values. Right? This is something you probably need to know how to do. Right, so that's a slight proof of it. And the mean square error over here. And if you want to find the actual mean square error, you just find the 2 parts, which is what we did already, and just plug everything in. Right? Because it's the same estimator from before. Now, the whole idea of the mean square error was to compare estimators, right? Because the goal is to be able to find a fairly good estimator. So we have this idea of comparisons. We have 2 estimators, and we say one is better than the other if the mean square error of it is smaller, right? Because it's an error term, you obviously want the error term to be smaller, right? The smaller it is, the better. As you can see here. So we'll go through an actual example. If you consider the first estimator we did before, right? So they just tell you what the mean square error is. And now we're going to compare it to some other estimator, right? This is the sample average, or sample mean, I should say, sample mean. Right, and this question is saying, okay, for what values is the second estimator better than the first? Right, so to do this, you need to find the mean square error of the second one. And to find the mean square error of the second one, you just find the bias and the variance. And this is just, well, from the fact that the mean of an average is just itself, and the variance of an average is just sigma squared over n. Right, sigma squared is lambda in this case. And so you have these 2 values, hence you can find the mean square error. Right, because you just squared this term. With 0 squared is 0, 0. So let's just write out 0 squared plus lambda over 7. So we know the mean square error of our second estimator and our first one as well. So we directly compare the 2. Since we want to find where the second estimator is better than the first, you make the second estimator's mean square error less than the first one's. And you just find the range for where this is true. You rearrange this and you'll see that it's actually just lambda on 28 greater than 0. And that's the same as saying lambda greater than 0. Right? And then if you remember from before, this is all around xi plus on lambda. So that's what lambda is. So in other words, it's for all lambda. For all values of, for all possible lambda, I should say. Because lambda can only be positive. Right? So the second estimator is always better than the first one with respect to the mean square error. Right? This isn't always true necessarily. It depends on what the parameter could be sometimes. Right? In this case, it was a fairly straightforward example. It could be like some reason from 1 to 3, one estimate is better than the other, but from values smaller than 1, bigger than 3, the second one is better, right? And here's just an example. It should be technically C hat. Yeah, just an example from there, should be fine. Now, we'll move on to some, I'll just mention convergence slightly. I know you went through the previous, what do you call it, seminar. I'll just mention it because it's kind of important in this one. So convergence in probability is just kind of this thing, right? It's the limit of the probability. So in probabilistically speaking, if the sequence were to go to infinity, there aren't going to be two different from one another, right? Because notice it's for all epsilon greater than 0, right? And the way we denote it is this. You just write your sequence thingamajiggy, and you just put an arrow and put a P on top of it, and it goes to Q. Oh, not Q, whoops, theta. Right. And you can probably see from here, it's kind of annoying to directly prove this, right? Because you have to worry about limits, you have to worry about like epsilons, and that's kind of annoying. So we actually have what do you call this? A sufficient condition, right? So something that if is true implies it converges in probability. It's this thing, the mean square error, right? We saw before the mean square error is actually relatively easy to find, given the estimator is kind of simple, right? Because you just need to find bias and variance, as you can see here. And if you can show this whole thing goes to 0 as n goes to infinity, then you show that something, sigma hat n, converges to sigma of theta in probability. Okay, let me write that again. Probability. Right, and this is a quick example. Right, the variance is just this thing, bias is just this thing, because it's unbiased. And you can clearly see this goes to 0, because sigma squared is a constant. Well, it's finite, and as n goes to infinity, this obviously goes to 0. Right. And hence, we show that it is convergent in probability. Right, this is fairly straightforward, so you can see how much easier it is. Right, the next important kind of convergence is in distribution. Right, so the ideal distribution is that, well, the distribution converges to some other specified distribution. Right, this is how we denote it. Similar, just use D instead. The one in particular we're going to be focused on in this course is really just the normality one. Right, so normality, and the way we do this is pretty much through standardization. This looks a lot like the CLT in the sense that this could be interpreted as your mean, roughly speaking, and this as your variance. Oh, okay, no, standard deviation, I should say. Standard deviation. Right. It kind of looks like what do you call it? It's not standardizing. It kind of looks like you're standardizing random variable, right? And that's why it converges to the standard normal random variable, right? And just remembering that makes it pretty easy to remember because it's very familiar to what you've seen before. And we have CLT, which is the standard old average or sample mean converges to normality when n goes to infinity. Right, sample size goes infinitely large, your distribution, your average distribution, goes to normality. And this second theorem, it's not something I think you need to overtly remember, but it is used to justify some of the things you do, right? In particular, this thing. This thing allows you to, this is the theorem that allows you to plug in, oh yeah, just let me replace this. It lets you plug in estimators into standard error, right? Because if you recall earlier, I mentioned something about like how the standard error is actually dependent on the true value. And since that's not really useful because we don't know what the true value is, sometimes you just plug it in. And the reason why you can do this is because of this theorem, right? So that's nice to know. And we'll just go with delta method. Okay, go over this real quick because I believe you might have went through this in the previous seminar as well. Right? The idea of the delta method is that if you have convergence in normality of this form, right, all you really do is if you want to find the convergence of g theta n, so some sort of transformation of your original random variable, all you do is, well, you just kind of sub things in. So you minus g theta and you just divide by g dash theta. And the most important thing to note is that it must be differentiable at theta with non-zero value. Right? You have to make sure this is true because you might lose a mark if you don't state this somewhere. Right? And this is quite nice because it makes sometimes finding something like, so we'll go for an example actually. You just see. We'll go for this one. Right? So we will just go quickly over, we have a bunch of IID Bernoulli random variables. And we want to find this particular distribution. So we want to find, for some reason, the average times this one, so 1 minus average. But this could be hard to find directly because it involves, well, a squared version and it involves like a bunch of sums and stuff like that. So we're going to do this in an indirect way. We're going to note the fact that this thing we know by CLT converges to normality. Normal mu sigma squared on n. Right, we're going to take advantage of that fact, as I did here. Right, since xn is just, well, xi is just Bernoulli, right? So you just find the expected value of it and the mean on the expected value and the variance. The variance is just this thing. You divide by n because it's an average. And you square root it because standard deviation. Now we know that this is true. This is in the form of sigma hat minus sigma theta over sigma over square root n converges to d, normal 0, 1. Right, it's in the required form we need. And so all we need to do is consider the transformation gx 1 minus x. Oops, 1 minus x. Right, because we know this is our goal. So we want to transform this thing into that. And the way to do it is to sub in this function. So do that real quick on yn. And we also must know what the g dash is. And then you just plug it in. As you can see here, this is gyn minus gp. And this is g dash p. Right. Not too complicated to calculate at all, right? It was very straightforward because we just used CLT and from there delta method, right? You didn't need to do it directly. And since we're doing asymptotically, that's fine. Right? Now, since we want a distribution of yn times 1 minus yn, we should make it the subject, right? So we can properly find the parameters. Right? And thanks to the properties of normality, you just bring this thing up there. And that's just, if you were to bring that into the variance term, you just square it. As you can see, it's just this square. Right? It's a nice property of normality. And then for the mean, right, for the constant term, you just shift over. You just bring it, this thing, into here. And so you have this. Right, just properties of normality. And so we found the asymptotic distribution of yn times 1 minus yn. That's pretty good, right? Now we need to check some other condition. I kind of skimmed over it. We must also check that the derivative at the mean value from before is non-zero. Right? Because if it was 0, this method doesn't work. And so you might have to do some other approach. Right? So in other words, p can't be equal to half. So, asymptotically speaking, this random variable converges to normality for these values. Right? The reason why 0 and 1 aren't included is because if it was 0 and 1, it wouldn't be a random variable. It would just be a constant 0, right? Because if p equals to 1, that implies that xi equals to 1, no matter what. And since the average in that implies x n bar equals to 1, right? And so this thing will equal to 0, so that's a constant. It's not a distribution. So that's why I excluded 1, and 0, the reverse case. Right. Now we move on to confidence intervals. Okay. So the idea of confidence intervals is that so far up to now we just talked about kind of estimators of random variables. We didn't really mention the true parameter itself. The idea of a confidence interval is that we want to establish some sort of range for which our true parameter would lie in with a given probability, right? Because we want to know the true parameter. And the way we'll do it is we'll base it on our estimators, right? So some statistics. As you can see, this is lower and upper bound. And so this confidence interval just means that the probability of this parameter being in this interval is equal to this percentage. Right? Notice that this and this are the same. And so the confidence interval is this. If you look at this definition, you can kind of see that the confidence interval is very generic. That's why they kind of say generic up here. What I mean by this is that it doesn't really matter what your lower and upper is, so long as the interval itself is this probability. So like if you imagine some sort of, okay, I'll go here. Like for example, normality, for example, right? You could technically just go this. So this is 5% for 95% confidence interval. Or you could do the one that you're more used to. You can do 2.5%, 2.5%. Right? And overall, this whole region in the middle is 95%. 95%. Right? And you can clearly see that if I were to shift the left and right side, so long as it adds up to 5%, it's still a confidence interval. Right? Right? So there's a lot of possible confidence intervals. It's just that the easiest one is usually one-sided or even split. Right? So yeah, that's why you usually see those. So we'll go through an actual kind of question of this. And I think I forgot to mention this. And since it's so general, the method to find the confidence intervals is very dependent on your random variable. Right? I think your assignment had like a gamma or something, and you can see that method was completely dependent on the fact that it's gamma. Right? So you need to kind of know your distributions well. But luckily for you guys, I think it's mentioned in your exam preparation that the question would guide you through that if it was not normal. Right? So I'll go through a slight question about this. So we're going to deal with a uniform random variable. And naturally, we want to know what this parameter is. Right? If you think of a uniform random variable, right? This parameter, theta, is just the maximum. Right? It's absolute maximum all these observations could be. Right? So a natural estimator of it would be, well, to find the max of all your observed values. Right? So that's why we consider this particular estimator. Now this question has two parts. You want to find its density, and after find an exact 95% confidence interval for theta. Right? So we'll do the first part first. A density for this. Right? This is probably something similar you've seen before in the previous seminar. So I'll briefly go over it. Maximum, right? So that means all of them must be less than or equal to x, right? This is the CDF. The reason why I work with CDF is because I know PDF equals to derivative of CDF, right? So if I can find a CDF, I can find a PDF, right? So I'll go over this. This means all of the random variables are small or equal to x, right? Because that's what max means. The maximum of all of them are small or equal to x. That means all of them should be. Here we use independence because we assume they're IID. And then they all follow the same distribution. So you just power n of it because there's n of them. And here you just use the fact that p x1 small equal to x equals to x on theta for x smaller or in 0 theta. Right? I didn't include this part because you're pretty much assuming that x is going to be in those interval anyway. Oh, I know I did include it. But yeah. Right, so we know the PDF, CDF, so we can find a PDF. Just differentiate. Right, and differentiating this is easy. Just make it so it's xn on theta n. Right, d on dx. And then you just differentiate x. And you got the CDF, or PDF, or density, as they call it here. Right, that should be fine. Now, we want to find an exact 95 confidence interval for this theta. Right? You can't use the normality kind of shenanigans that they do because, well, it's not normal in this case. So you're going to have to somehow use the information from before to build your interval. As you can see, this is highly dependent on the distribution itself. Right? So if you read this here, right, we want to find a 95% exact confidence interval. And you need to kind of have some sort of intuition as to what the parameter represents if you want to kind of build a proper confidence interval. In this case, theta represents the maximum, right? And since the question asks for the density of xn, so the maximum, you're going to somehow use that in your answer, right? Makes sense. So if you kind of just imagine the PDF, so I'm just going to draw it. It's probably going to be really ugly, but draw it real quick. Okay, if this is the PDF, so it looks something like this. Now just draw in green. This is theta, this is 0, right? So this is the PDF of xn. So fxn equals to n theta n, x power n minus x, minus 1, right? Right. We want to somehow build a 95 confidence interval, percent confidence interval for theta. We know that the upper bound of xn is theta, right? So you wouldn't really go with a two-sided test here because you would expect theta to be like a maximum value. So it doesn't make sense to look at both sides in a sense, or it doesn't make as much sense, I feel like. So what I'm going to do is, I should probably extend this up so it's easier to see. Yeah, just pretend it's like this. I'm going to look at a one-sided test where this is 5% here. Right? And I'm going to find a point here such that that is true. So a z, such that this is true. Oh wait, did I choose z or a? I chose a, okay. A. A 0.05. Right? So that's the reason why I kind of look at this particular region, right? Because I know I want to find the critical point such that this is 95%. And the reason why I look above is because, well, that's kind of what the interpretation of theta is. It's the maximum. So I don't want to look for the minimum or anything like that. Right. So if you do this, right, and here we just use the CDF from before, right, probability xn smaller equal to z equals to z on theta to the power of n, right? This is from the first question. So greater than is just 1 minus that, right? Here I'd use a 0.05 instead. And I rearrange to make a 0.05 the answer. All right, so I can find what it is. Right. And you can clearly see it depends on theta. So that's good, right? It depends on theta. So if we were to go back into it, so we sub it back in, right? That's what this is. You want to find an interval for it. So you want to make theta in the middle of your interval. So I'm going to make theta, I'm going to bring theta to the left side, as you see here. And you can see that this is just reciprocals. And you can clearly see that this is equal to 95%. Right? This is pretty good. You have a right hand side. All you need is a left hand side now. But if you consider what theta means from the definition, theta must be positive because it must be an upper bound. And since the lower bound is 0, lower bound, then that means theta must be within this interval. Right? That's where this random kind of, well, not really random, but that's where this 0 shenanigans pops up from interpretation of theta. Upper bound, lower bound. Upper bound must be greater than lower bound. Right? And so this is literally just the definition of an exact confidence interval, right? We know a lower bound and an upper bound such that the probability that the parameters inside this interval is equal to 95%. Right? And hence this is an exact. It's not the only one, right? Because as I mentioned like way earlier before, there's infinite number of confidence intervals, right? You just shift things over and it'll still be a confidence interval. It's just that this is the most intuitive way to do it for this question, I feel like, because of what theta means. Right? So as you can see, it's highly dependent on the distribution and good. And so you need to use the information hinted to you within the question before, because it's got to be broken into sub-questions, like in your assignment with the gamma. Right. So exact confidence intervals in general are very it may be annoying to deal with, right? So like everything else in this course, right, we say, well, we make it easier if it's normal. Life is easier if it's normal, right? Because normal is really nice. And it turns out the confidence intervals that you build is also really easy in a normal distribution, right? An exact confidence interval. So we'll go through that. So before we can actually go through that, you need to I'll go through some preliminary shenanigans. So it justifies why we can do what we did in this instance. So we need to consider something called a chi-squared, right? This becomes more important in 2931 as well. So it's good to know it. You don't really need to remember this. You should probably remember this thing here. The fact that it's a gamma with these parameters, right? It's not too hard to remember, right? Just remember there's a 2 somewhere and then just divide by 2 and then 2. Alright, and from there you can just figure out this anyway, because you're given the PDF of a gamma. Right? Now, the important thing to note about the chi-squared is mainly where it comes from. It comes from the fact that it's a squared of a standard normal. Right? And since it's a squared, you might be remembering of SX. Right, it's a squared term, and the only kind of squared term that comes to my head, firstly, is the sample variance. So it's probably going to come into play there, right? And it does, but yeah, that's probably there. And the other thing is that if you were to sum a bunch of chi-squares that are independent, the rates, so you just add them up. You just add up the degrees of freedom, right? So it's really easy. You just go okay, independent, well, I'll just add the rates themselves, right? And that pretty much comes from the fact because it's gamma. Wait, no, I shouldn't say that. Wait, no, I take it back. Right, just go to that. Right, and here's just a very simple example. Right, you can see that we have a bunch of IID normal random variables, or standard normals. And now we want to find the probability that this is true, right? Before knowing those facts, it would be kind of annoying to figure out what this is. But we know that Zi is independent standard normal. So Zi squared is chi-squared 1, right? And since Zi is independent, that implies that I squares are also I independent of each other. Right, and so you can just use the fact that, well, everything is chi-squared 1, and they're all independent of one another. So I just add up the degrees of freedom. That should be 6. Right, there's 6 of them, and so 1 plus 1 plus 1 plus 1 plus 1 plus 1 equals 6. Right, there's 6 ones. And it turns out this is some R shenanigans. Right, and it turns out to be 0.01. Yeah, we'll just skip through that. Now, this is the next thing. You don't really need to know it per se. It's more important in 2931. You don't really need to know this distribution. Don't really need to remember. But you should be kind of aware of it because it has some nice properties. Right? It comes up in your hypothesis testing and confidence intervals. Right? The reason being is because essentially you have this property, some sort of square root shenanigans where it's standard normal and you have Q that's chi-squared. And if they're independent, then you can build a t-squared distribution. Oh no, not t-squared, a t distribution. Now, if you just focus on this thing here, this looks kind of like the standardization process for normal. It kind of looks like it, right? Or it kind of looks like CLT, I should say, to an extent, right? And that's kind of where it pops in later on. And yeah, that's pretty much it. And you should also note the distribution is even, so symmetric about 0, right? Because this is important when building your what do you call it? Confidence intervals. Right, we have the sample variance. Right, the reason why we bring this up again is because it pops up later on. And the point you need to know about this, it says a -1. And that's pretty much because this thing is an estimator of mu. And so we have to kind of reduce or increase the variance of our answer. Right, because you decrease the numerator, you increase the whole thing. So that's kind of where that -1 pops in. Right. Now, we have kind of this thing here. Right, so the sample variance, if you were to consider a normal random sample, right, with some sort of unknown mean and variance, if you were to just look at the sample variance itself, oh no, what happened there? Okay, oops. Right, so sample variance here, you can actually find a distribution of it in this form. Right, so s squared over sigma squared is actually chi-squared n-1. This n-1 thing is just to make things work, really. Right, and now this is kind of the most important thing out of everything before. If you have a bunch of IID, normal random variables, but you don't know the parameters, or you don't know the, what do you call it? The variance, unknown. What you can do is essentially you can just plug in your sample variance, but the distribution won't be normal. It will be something similar. It will just be t, and you have to note that it's going to be n-1 degrees of freedom. Right? The reason why is pretty much you can think of it as you're replacing a true value. Replace true value with estimator, right? And that kind of leads to a change in the what do you call it? Degrees of freedom, right? So it's similar reasoning as to why this is n-1, intuitively speaking. Same kind of reasoning. So, and you note this is an exact distribution, right? And this is very useful because if you know this is exact, you can build exact confidence intervals, right? And since the normal only depends on these two parameters, you can deal with basically any normal distribution, right? You don't care because, like, let's suppose you don't know, you do know you do know sigma squared. Well, you just use normality and build a confidence interval based off that. If you don't, then you use the fact that it's t distributed, right? So you can see it becomes really nice, right? Now, I guess the biggest problem that some people might have is that you should only use this if the original sample comes from a normal distribution or something that's very similar, right? Because this is everything is based upon normality, right? So if it wasn't normal or it wasn't asymptotically normal, you can't do any of the things you did above, right? And so you have to do the weird thingamajiggy I did with the uniform random variable. And this is just some notation, right? -1. So alpha just represents the percentage. So you look at the distribution. Here, t n minus 1 alpha. Here, this region here would be alpha. Right? Just notation. It doesn't really matter how you represent this. The only thing that matters is kind of if you keep it consistent. Right? You could potentially like write this as 1 minus like alpha, but that's kind of counterintuitive, I feel like. So it's best to kind of keep it in this form. So, like all that shenanigans above is basically to lead you to these two results, right? This is if you have a normal random variable sample, we can build very easy or very intuitive confidence intervals by just looking around the sample mean, right? So we can do that for no matter what. So you either know the variance or you don't. If you do know the variance, which is this blue situation, you use the normal distribution, and you just use the actual value. If you don't know it, you use the t distribution, and you sub in your sample variance. Right? So they're basically identical. You just kind of replace things with whatever. Right? Don't know, you replace it with the t distribution, and you use the sample variance. Right? And these can be derived on the spot. Right? The derivation isn't too bad. I'll show that later. It pops up later. Right. So we'll just go through a quick example. So we have these 3 data points. And we want to find a 95 confidence interval for its mean. Right? If you look at this kind of question, you read through it, it doesn't state what the actual theoretical theoretical variance is. Right? It just says you collected data from normality. It doesn't say anything about the parameters. So you have to use the exact t confidence interval. I guess that's what you will call it, confidence interval. Right, so you can't use the first one, you have to use this one, because we don't know what the variance is. And so we have to find the sample variance, which is kind of just plugging numbers in. It turns out to be this. And from here, you have to note there are 3 observations, so n equals to 3. So the distribution we consider is t, oh no, what was that? Tn minus 1, which equals to T3 minus 1, which equals to T2. Right, so the distribution you consider is T2, and here it's 0.975, because here alpha equals to 0.05, split this into 0.025. So you split it across two ends of the distribution. Right, and that's why you have that top and the bottom end. And this is how you write it in R. And so we have this value, which is just subbed into here and here. And this value over here is just the, let's go back up, is just the sample mean. And the value over here is just this thing. Right? So you can see it's just plugging numbers in. It's not too bad. Right? And we found a 95% confidence interval. And I guess the last thing you should note is the fact that this is free. So number of observations. Right? It's not 2 because the -1 thing only applies to the distribution. Doesn't apply to anything else. And you just plug numbers in from there. Right. So that's confidence intervals. And as mentioned earlier, if you have asymptotic normality, you can just kind of do this. It's the same thing, right? So you find the estimator, variance, or standard error of the estimator, and here we use the Z distribution, so normality. Right, so you just pretend it's normal in the long run, right? You just assume that you have a bunch of observations, and hence it's normal. So we just kind of plug it into the normal setting. Right, so it's literally just the same thing, just plug in your estimators instead. Right. Let's plug it in. As you can see here, this is an example, right? I guess the important thing to note is that this is, oh, what's that? What is that? This is the estimator of the standard error itself. Right. And I'll just quickly go over this example. So an example of this is, let's suppose we want to find a confidence interval for lambda, so in a Poisson distribution, right? But we don't really know how to do it exactly, because again, it completely depends on the distribution. So we're going to settle for an approximate confidence interval, right? And we know we consider this estimator, so the sample mean. The reason why we consider this is because you want to use CLT, and we also know it's unbiased anyway, so it's pretty good. Because the mean of Poisson is the parameter. Right, so that's pretty good overall. And by using CLT, we know it's asymptotically normal. And so we can just kind of pretend it is normal and just kind of plug things in as if it were normal. Right, and this is kind of how you would do it. Right, you know it's normal. Right, or you know it's asymptotically normal, right? And so, by noting the fact that, let's see, if I have to draw it out, this is your normal distribution. This is 2.5%. So is this thing over here. Right? And now, the reason why you consider this form is because it makes sense for a normal distribution to be symmetric. Okay, right. It makes sense to use a two-sided test for a normal distribution because it's symmetric, right? And the interpretation of the mean is just in the middle. So it makes sense that you want to use a two-sided test. So here we just kind of set up our random variable so that it's in between two values, equally distant, right? So these two are the same thing. So just negative z and z, not 0. Such that this is 95%, right? The probability that this interval is maintained is the probability that this random variable is in this interval is 95%, right? Now, since we want a confidence interval, we want Ci or lambda, all you do is, well, you make C lambda the middle term, and you can see, if I were to kind of erase all these red things here, it's not too difficult because lambda is literally only in the numerator. Everything else is lambda hat, right? So that's a estimator. So you just rearrange, so just focus on this thing here. And we note that since the normal distribution is symmetric about 0, the 2.5% region here is just a negative version of the 2.5% region up here, right? So just negative of it. And this is just for convenience. Here, we just multiply both sides by this thing. Let's bring it up. Since it's positive, you don't need to change the signs. Here, since we want to make lambda the subject, I'm going to times everything by -1. That's a -1. Right? And so the inequality will flip, essentially. Will flip. Right? So this thing would go over here, and this one would go over here. But you notice that it doesn't really, because the negatives cancel out, right? So it becomes kind of, it looks very similar to the previous thing, right? But in general, you need to be careful when dealing with inequalities, when you multiply by negatives, because you need to flip things over, right? And then here, all you need to do is make a lambda subject, so you plus lambda hat to both sides. And so you have this. You found a lower and upper bound. And remember, this is done within the probability, yeah? And you didn't change anything else, right? So the probability should still be 95%. So the probability of this thing should still be 95%. Right? Hence, we have found, so that's what this is, a 95% confidence interval for our parameter. Right? As you can see, it's fairly straightforward because it's literally just assuming that this is normal and you just work from there, right? Using asymptotic normality. So I'll probably right now let you guys take a 5-minute break. Yeah, let you 5-minute break, right? Because we're about halfway through. And we'll follow up from there. Right. If you guys have any questions in particular, feel free to just type it. And I'll probably answer it. No, not probably. I will answer it as fast as possible. Right. So I'll just mute myself for now. Yeah, might as well. Alright, so just might as well start up again. Right, we'll kind of start now. So the most recent thing we did was this thing called asymptotic normality, right? We just use the fact that it's asymptotic normal, so we can build a confidence interval based on that. Now, so before we found the theoretical value, right? Notice up here, this is all theoretical, right? We didn't actually sub in any numbers. So if we just do the same question, but we actually give some observations now, we can just sub in numbers, right? So the only thing that depends up here on its parameters is lambda hat and n. So those are the only things we kind of need to sub in. Oh yeah, I guess these two also. These two are just fixed values, 1.96 and 6. Right? So we need to figure out what lambda hat is. And lambda hat, if you recall, is actually just the mean sample mean. So just kind of average everything here. And so you'll get this over here, as you see here. Right? And n is equal to 30. So you just sub 30 into the denominator, because n was over here. Right? So from here, just plug in numbers. Right? So if you can find the theoretical mean or confidence interval, everything else is fairly straightforward, just subbing numbers from there. Right. Now, some behavior. Okay. So the behavior of a confidence interval, well, okay, intuitively speaking, if we increase n, so we add more samples, right? That just means we have a lot more data to work with. And so we could be more strict with as to, okay, we can be more confident in our answer, right? So more data can be more confident. Confidence in region. And so we can shrink our confidence interval, right? And that kind of links to this in an extent. So 99% confidence interval is wider than a 95% confidence interval. Well, that's really just because to attain higher confidence, you just make your region bigger. Make region bigger, right? Because if your region is bigger, then it's more likely that the true value is going to be within the region, right? Obviously, you don't want to make it too big because it's meaningless, right? So you need to strike a balance between the two. Right. So we'll move on to this part here. So before up to now, I don't think I ever mentioned how we find the estimators. I kind of just mentioned like, okay, so we have an estimator, right? We're going to build a confidence interval. We're going to evaluate it. It's mean square error, stuff like that, right? Now, we're going to consider two main methods, right? The first method is the method of moments. The intuition behind this one is that suppose you have k parameters for your distribution. Since the distribution is dependent on these parameters, right? So for example, let's suppose xi is gamma, alpha, beta, right? If you know alpha and beta, you know the whole distribution, right? So the goal is, well, I just estimate these two parameters, right? And that should be a good fit overall. And the way we do it with the method of moments is, well, as the name suggests, you look at the moments and compare them naively to some other version, right? So as you see here, naive estimator, right? You compare the true value to a naive estimator, and you do it for k equations, so k parameters, because you want to solve k simultaneous equations to get k unique values, right? Oh no, to get a unique solution, I should say. Right, that should be fine. Right. And this is just a brief slide about like how estimate and estimators are different, but that's not too important really. You can just work with estimators, right? I don't think Glebo cares about that. You just kind of like put capital X in. It should be fine. So here's a question about this. So we consider a bunch of random variables that follow some sort of distribution. I think this is called what do you call it? Pareto. It's a Pareto distribution. Right, that's not too important. Now you want to use the method of moments to find estimator for theta. Right? And the first question you should ask yourself is how many parameters there are, because the number of parameters you have influences how many equations you build up. Right? And obviously this question is just kind of, well, in this question there's only one parameter, theta. Right? As such, there's only one parameter, so we only go up to the first moment. Right? If there are two parameters, you'll go up to the second moment. Right? You consider this thing as well. Sine squared. Right? But there's only one, so we don't worry about that. If two parameters. Right? So to do this, well, this side is easy to find because it's literally just values you found. You just need to figure out what the theoretical mean is. So theoretical versus estimated. Right, so we just need to figure out what the theoretical value is. So we're going to do that. They give you the PDF and they give you the range. So you just sub in that bad boy, right? So it's just 0 to 1, x, f, x, x, dx. Right, so you just sub it in. And that's what they did here. X, x, and fx, fx. And here you just kind of use integration, right? Notice this is a very simple integration. Bring power down, and you end up with this. So now you have the theoretical mean, right? And clearly it's in terms of the parameters, or the parameter in this case. And so you just match up the theoretical versus the estimated. And you just rearrange to make theta the subject, because we want theta hat. Right, you want to build a theta hat based off this. Right, so just rearrange, make theta the subject. I guess technically this should be theta hat throughout. Right? And then, since it's an estimator, it should be a random variable, or function of random variables. So we just, rather than keeping as little x, as you can see here, we make it big X. Right? Technically speaking, you could have just made it big X to begin with. Like, you could have just made this big X to begin with. And yeah, that's pretty much what I did. Of course, I just kind of used big X to begin with, so I wouldn't forget to make it big X at the end. Similar with the likelihood ratio, or likelihood test. What's the maximum likelihood? Right? And some properties of it actually turns out to be consistent. So convergent probabilistically. And it turns out some nice conditions, it's also asymptotically normal. So that's quite nice, right? Because if it's asymptotically normal, you can build very easy what's it called? Confidence intervals. Right? So that's quite nice. These two are quite nice. But we can't only consider one method, because if you recall, the method of moments estimator kind of just looks at it from a single perspective. It's kind of like a dot point comparison, right? Obviously, the mean and the moments influence the distribution, if you know what a distribution is. But we want to kind of consider some estimation method that has a punishing term, right? Because it's good to be able to compare models against one another and see which one's better and worse according to some criteria, right? So we want to punish. And the punishment is if observations are very unlikely to happen, so they have low density values, right? So the PDF is very low at that point. then that means we wouldn't really opt to go for that model, because it's really unlikely that you would have had that distribution based on your sample collection. Right? And the way we do this is by multiplication. Right? We just multiply all the PDFs at each of the individual random sample values. Right? So if there's a value that's really small, so if very small, that's going to drag down the whole likelihood down by a lot, and it's going to make it less desirable, which makes sense, right? So if you have a lot of those things, it's really bad, right? Now, so based off this, we want to find the maximum likelihood, right? Because the idea is, well, if all these values, if you maximize likelihood, right, that means each of these values, the f's, are fairly big, right? So it's fairly likely that these observations would have occurred if our parameter was at, well, if our distribution had that particular parameter, right? So we want to find the MLE, so maximum likelihood estimator, but since it's so hard to differentiate a product, right? Like imagine like n products, differentiating will be a pain. We want to basically break it down to a sum, and likely good for us that the log function serves that exact purpose, right? It breaks it down to a sum, right? Logs break products down to sums, and another nice property of the log function is that it's strictly increasing. Right? Since it's strictly increasing, that means if we maximize the log, maximize this, we maximize the likelihood itself. Right? They're 1-to-1. So that's really good. So we can deal with differentiating a sum instead. And since differentiation is linear, that's really a lot more straightforward. And this is some kind of terminology. We call sigma theta MLE, and also maximize the likelihood. Right, that's fine. So we'll go through an actual example, right? Because everything before was just kind of blah blah about the reason why we do things. Right, so we're going to consider a simplified kind of distribution, a log normal with one parameter unknown. Right, since there's only one parameter, it's a lot easier. If there's two, you have to use Hessian, but you don't have to do that in your exam, it seems like. So just deal with one. And it has this following PDF. Right, this is given to you. So now you want to find the MLE estimator of sigma. Right, so what you do is you find the log likelihood, as you can see here. So the log likelihood is just, well, the summation of the logs of the individual PDFs. Right, notice that this thing is just the above squared red term. Right, just something's in there. Now, since we want to find, this is basically a function in terms of sigma. Function in terms of sigma, G sigma. Right, so you're basically only focusing on sigma because the x's are essentially constants from your perspective, because you collected this data already, right? So they're constants, you can't change them. The only thing you can change is this sigma over here and this sigma over here. So since it's a constant and we're talking about maximization, you can pretty much ignore it, right? And the way we're going to do that is basically shoving all those things into a constant term, right? The reason why this works, so if you look at this part and this part here, if you were to use the log function, so the log function would be something like log x sigma square root 2 pi 1. This will just be equal to negative ln sigma minus ln x root 2 pi, right? I just shove all these things into C because it's independent of sigma, right? And sigma is the only thing I can change. Now I can't do it here with these things because, well, you can see that this completely depends on sigma, so I can't get rid of the ln xi squared. Right, and all I really used here was the fact that these are inverse functions, ln and exponential, so you just end up with the term inside. Right. Now we want to maximize this, right? And it's a continuous function with respect to sigma as long as sigma is greater than 0. So the way we do that is by differentiation. Right, just differentiate it. As you can see here, differentiating this is just this thing. Differentiating this, -2, the 2 cancels out, the negative cancels out as well, makes sigma 3. Right, so you found the derivative. Now you set this to 0, so you can find a stationary point, right? That's what I did. I did sigma hat, I subbed in the sigma hat so that this is 0, and just rearrange, and eventually you find this. Very quick, right? Just bring this over, times it up, times this down, and you end up with this thing. Now, we found a stationary point, right? So can we just say that this is just the MLE? This thing here. MLE. Right, can you just go like, okay, we found the MLE, we're done, we're good, we're good to go. You can't technically do that because really what you found so far is a stat point. Right? In nature, you only found a stat point. You need to prove it's a maximum. Right? So we need to check it's a maximum. And for stationary points, you just check the second derivative and check the sign. Right? So I just found the second order derivative. Now, in this case, it's not very obvious that this is negative for every sigma, right? Because it depends on x, the given x's. So you're going to have to sub it in. So we're going to sub in our value that we found before. So put sigma hat in. Now here, since we're only interested in the sign, I'm going to factorize anything that's positive that's within both fractions, right? So that's the sigma squared thing here. So this would be 1 on sigma hat squared n minus 3 summation 1 n ln xi squared over sigma hat squared, right? All I did was factorize out this thing because that's always positive, so it's not going to really influence my answer. Now, if you recall, you have to recall what sigma hat squared is. Sigma hat, oh whoops, happened there. Okay, sigma hat squared is equal to this that we found before. Is equal to this thing, right? And if you look at the numerator, you can see that this summation of the log squared things, is a constant factor across the two, so it's going to cancel out, right? And in fact, if you were to rearrange things, you can see that it turns out to be this, -3n. Right? The 3 is just from the fact that this is a 3 here, and this whole thing is just n. This is just, okay, let me just erase that because that's really ugly. And this whole thing, this whole kind of thing here, is just n. Right? Interesting sign, let me get rid of that. So, because we just rearrange and divide both sides by sigma squared. Right? So we found the term. Right? So sometimes you have to be a little tricky with your summations, stuff like that. You have to sub things in. And then here we note that -2n, this is positive, so this whole thing must be negative. Right? Because negative over positive number is negative. Right? Hence, it is a maximum stationary point. Right? That's good, right? We prove it's a maximum stat point. And then you just kind of like, it's kind of implied that since it's the only stationary point and L sigma x is continuous for sigma greater than 0, right? Since it's a unique maximum stationary point, it's also a global maximum. right? You don't need to say any of these things, like that last part I mentioned, how it's a global maximum because it's a unique maximum stat point. But it's kind of implied. If there's multiple maximum stationary points, you obviously need to compare which one has a higher value, right? But I highly doubt what's going to happen. And so we can say this is MLE, but since it's an estimator, you need to make a random variable. So you see this little x, just make it big. And bam, you're done, right? That's your MOE. So that's how you would find an MOE. You just find the log likelihood, differentiate, rearrange, check second order derivative, right? You have to check this thing. Make sure you do that, because if you didn't, then you might lose a mark there. And then, yeah, from there you would show its MOE. Now, properties. Now, some of the MOE is better. I feel like the MOE is better than the method and moment estimator because it has more properties that are desirable. It has this equal variant property. So what it means is that suppose you're interested in some parameter. For some reason you're interested in this thing here, sigma squared e sigma over 10 theta. Right? You want to estimate this. For some weird reason you want to estimate this. As you can see, it's very complicated to estimate directly. Right? So you probably don't want to do that. But with this property over here, yeah, if you find sigma theta MLE, all you need to do is sub it in, and then you have the MLE for g theta as well. So if I want to write out, it will be g theta MLE equals to g. Let me write that again. G theta MLE. Right? So the MLE subbed in is the MLE of the function itself. That's a really nice property because it makes finding certain estimators really straightforward. The next very nice property is asymptotically normal. Again, that's really nice because normal is good. Consistent, that's good as well. Now, asymptotically optimal. This is probably the biggest one. What it means is basically keep in mind estimators are random variables, right? So you want to make sure that the variance of your estimator isn't very large, right? And it could reach some sort of optimal point, right? And the MLE turns out to actually be it's able to reach it asymptotically speaking, right? So min, okay, whoops, I shouldn't say min. Okay, can reach, I think it's called Cramer-Rao lower bound, right? It can reach the Cramer-Rao lower bound asymptotically. Right, so that's really good because, well, if your estimator is not that variable, it can achieve a minimum variance, then you don't need as many observations to stabilize your estimator. Right, so you can use as data. Right, so now if you think about the MLE, right, it can be a very complicated function like this thing here. And finding the variance of this thing looks like a pain, right? Just imagine finding the variance of square root of a bunch of sums. It's like, okay, I don't want to do that, right? So we're going to consider an asymptotic approach to find the variance, right? And it's called the Fisher information. Right. Now, the Fisher information is really just defined as the expected value of the second order derivative of the log likelihood, right? The negative is just to make it positive, this negative thing here. And this turns out to be related to optimal variance. Right? I think it's like the inverse of it, the reciprocal of it. Okay, so now let's suppose we want to find this thing, right? We want to find the Fisher information. So all you do is kind of find the second order derivative. And, oh, I guess I should mention this. There is another definition for the efficient information, the squared of the first order derivative. But you usually don't use it because, well, if you square a sum, right, it's just going to be like a bunch of terms in between, and that's annoying, right? So you just kind of deal with the second order derivative. Because you're always going to find this thing anyway, so might as well use it directly. Right, that's why we don't consider the second one as much. So here we were given that this is true, right? This is something we found from the previous question anyway. And now we want to find its Fisher information. So sigma, I am sigma. Right, so that's what this is. So I'll just find the second order derivative, which is just this thing, right? Again, from the previous example. Just sub it in, or you can just differentiate it. Very easy to find. And in here, you can see that this is a constant, so I can just bring it out. So is this thing, and the sum, since expectations is linear, you can bring it out as well. Here I kind of implicitly use the fact that xi are iid, so then that implies so are the xi's, so are the ln xi's, I mean. Right, and so they have the same expectations, so that's why it's free n, so free n. Right, and in here, we note the fact that, as you read here, x1 is log normal, and this is kind of something you kind of just have to remember. The log of a log normal is normal. I know it's kind of counterintuitive with the naming scheme and all that, but the way I kind of remember it is the fact that I know x1 is greater than 0. To make it, well, so you want to convert it to a normal, right? The only way to make it normal is to make it go the whole real plane. So you either can log it or exponential it, right? Exponential is strictly positive, so this can't be it, right? And so this must be the transformation you need. Right, that's kind of the way I remember it. If you don't want to remember it that way, don't worry about it. But yeah, you just need to remember the fact that log of a log normal is normal. Right? So, and we use this fact here because it makes things easier. You want to find the log moment squared, right? But since we know the log of x is normal, this is just the same as finding, well, expected value of y squared equals the variance of y plus mu y squared. Right? Just rearrange the variance formula and you'll get this thing. But we know the variance of the distribution and the mean, because that's what the normal distribution has as parameters. Sigma, 0 squared. Just bring a sigma, and bam, you get this. Right, sigma 2, 4 minus 2 is 2. Right, and so you end up with 2n of the sigma squared. Right, and so you have found the Fisher information. Right. So move on to the next example. I'll just skip this one actually, because it's kind of the same thing anyway. Oh, why is this blank? Okay, so I mentioned earlier how the Fisher information is related to the variance. The reason why it's very related is because it's actually the inverse of the variance. Right, as you can see, it converges in probability to 1. So if you just rearrange it, that pretty much means the standard error of your MLE is the square root inverse of the Fisher information. Right? And as you can see earlier, the Fisher information, not too bad, not too hard to find. At least comparatively. Right? Than directly finding it through your MLE itself. Right, so for this example, we know that the Fisher information was this, so we want to estimate the standard error. Just reciprocal it, sigma squared of 2n, and that's just sigma over square root 2n, which is what you see here. Right, fairly straightforward, and this is asymptotic. asymptotically. So we found the variance asymptotically, and so we can find the variance of the MLE, and so we know that it's asymptotically normal as well, right? MLE. Oh no, what happened there? MLE asymptotically normal, and so we can just use the asymptotic, what's that thing called? Asymptotic confidence intervals for normality, right? And that's what this whole kind of thing is over here is about. If you want to find the confidence intervals, well, you just replace the standard error term with the inverse of the square root of the fish information. Right. I think this is meant to be unbiased. Right? It's also asymptotically optimal because it can reach the Cramer-Round lower bound for unbiased estimators. I believe that's what it is. Right, so that's pretty much estimation. Now, the very last part of the course. Right. So this is probably the most confusing part, I feel like, maybe. It's hypothesis testing. The idea basically behind hypothesis, you probably heard Libo say this, because this is how he explained it to me, is that it's pretty much a proof by contradiction, where you just add some uncertainty. Right? Uncertainty because, well, you're doing probabilities, right? So there's going to be some sort of uncertainty involved. And the contradiction part comes from the fact that you assume the null, and then base your argument based around that assumption, right? Right, and check it's probably based on the chosen alternate hypothesis, right? So the idea is basically, okay, let me just explain real quick. Let's suppose you choose some sort of null hypothesis, and then you build some sort of test on top of that. If it's very unlikely for that test to have happened, you can reject the null, because it's very unlikely that your initial assumption is true, right? So that's why it's a proof by contradiction per se. It's also part of the reason why we say fail to reject rather than accept most of the time, or we prefer to say that. Because technically, when you say accept, you haven't proven anything. You just said that, well, we don't have enough evidence to disprove it, right? That's not really proving. So, yeah, that's pretty much the reason for that wording. Now, since the null hypothesis is the thing we assume, it's usually the simpler assumption, right? Because who wants to work with harder assumptions, right? That's just annoying, right? So we deal with the simpler assumption, and in this course, it's usually just a single value. Well, I think it's only a single value. So HO is sigma theta equals theta 0. And the alternate hypothesis can be any of these three. And the way you build your test is dependent on which of the three it is, right? Because if you recall, this could be two-sided, and these two are one-sided, right? And so it's important to recognize which one is your chosen alternate hypothesis, right? So we just talked about p-value. Okay. The p-value is pretty much the thing, it's one of the two things, you can choose either or, things you would use to test the likeliness of your null hypothesis. And it depends on what your alternate is, right? So the general idea is the smaller the p-value, the more evidence there is against the null, right? Because if the probability of something happening is very small when you assume something, then that means your initial assumption is very unlikely to be true in the first place, right? So we can reject your initial assumption. Initial assumption. Right, very unlikely, then, well, that means your initial assumption is probably not true anyway. Right, so the way we do the hypothesis testing using p-value is basically, well, you firstly need to know your null, and your alternate hypothesis, then you need to figure out your test statistic and the distribution given that the null is true. You find the actual value of it, you find its p-value, and then you make a conclusion. Right, so we'll go through this step by step. Actually, no, before we do that, so some examples. The main hypothesis testing you're going to do is basically on normals. For exact hypothesis testing, it's going to be on normal samples. Normal samples. So in this version, you know the variance, alright? So you can just straight up use that it's normal under the null. And this is your test statistic. This thing is just from standardization. Standardized. Normal. Right, and notice how it's mu0, because under the null hypothesis, we assume, mu0, we assume that the true mean is mu0. So that's why you minus that as your parameter, essentially. Right, and if you want to do a two-sided test, right, so let's suppose we draw out the distribution. We know this thing follows a standard normal. Right. If we want to check the fact that mu is not equal to mu0, then you don't really care whether it's smaller or bigger than. So you're interested in the fact that the regions beyond your test statistic, so t here, or z, minus z, are greater than some value. Right? If these two areas add up to probability of z greater than observed value. So essentially this thing is greater than your alpha level. Then that means, well, you can't really reject your null because it's not super uncertain that that could have happened. Right? And the one-sided test, if you were to look at this example, right, all you do is, well, you are interested, you want to test whether or not the true mean is less than the assumed mean under the null, so mu0. Since you're testing the fact that it's smaller than, right, then you look at this statistic thing up here. If the mu truly was smaller than mu0, this value here would be negative. Right, you would suspect this would be negative because x bar is a consistent estimator of mu, right? And since it's consistent, you would suspect that this would get to the true value. So this thing would be negative overall, right? And that's why you look at smaller than, because of that fact. And the reverse is true for mu greater than mu0, right? You look bigger than because it's positive. Right. Now, just like with the confidence intervals, if you don't know the variance, you can't use the normal distribution. You have to use the t distribution, and it's the exact same kind of setting. Just replace the variance with the estimated variance, and then compare your distribution to t n minus 1 instead. Right, so the same thing as confidence intervals. So we'll go for an example of this. Okay, so basically the setting is you're recording the number of earthquakes since 2016, and now we want to check whether or not there have been more earthquakes these past few years. Right, so this kind of tells you what your alternate hypothesis is, right? So H1, H0. Here they tell you, if you just read the data, long-term records suggest an average of 16.25 earthquakes per year. Right, so our null is going to be the simpler assumption of having the exact number of earthquakes. Right. Now, if you look over the alternate, or basically what we want to check, right? We want to check if there's more earthquakes. We want to check mu greater than 16.25. Right? it doesn't make sense to check less than, because that's opposite of what we're trying to check. We're trying to check if there's more earthquakes, so that's our alternate because of that. So in this setting, we have a one-sided test. And here we can assume the data is normally distributed, so we can use these things up here. Right, either of these two tests. Right. So that's why we have this hypothesis, right? Want to check more than previous years, so that's why this is more than. Right, and now we want to figure out the test statistic under the null now. That's the second step, right? Now, since they don't tell you the true value of their variance, you can only estimate it based on the data, right? So you're going to use S, unknown variance. And just like the standard confidence intervals, the distribution is Tn minus 1, right? There are 4 observations, so n equals to 4. So this thing is Tn minus 1, which equals to 3. Right, and notice how we're doing under the null, so this mu becomes 16.25, because that's the null assumption. Right, just go over that. So we have the test statistic and its distribution. Right, so now we need to figure out the observed value, so what you actually see, rather than theoretically see. Right, all you do here is you sub in the actual numbers. Right, so I'll zoom out a little more. X bar, you lose the little x bar. Capital S, you use little s. Right, and these values are things from before. These are the sample mean and variance. And sample variance. Right, and you just sub those in. Goes into this thing up here. And then you'll see that this is the observed value of your statistic. Alright. Now, since we're doing the p-value variation of this test, we look at the probability that the statistic, so t, is greater. Okay, whoops, actually no, I should probably mention something first. Okay. Here we need to note what type of alternate hypothesis we have. We remember the alternate is mu greater than 16.25. Right? Since it's greater than, and if you look at this statistic here, it should be mu 0. Mu 0. The probability that this thing, so like if you are testing the fact that the mean, the true mean, is actually bigger than 16.25, right? You would suspect that this thing to be positive. But you can only reject that if it's massively positive, right? And massively depends on the context. In this case, it's dependent on the fact that it's a T3 distribution. Where is it? As you can see here, T3. So that's why we do a greater than this observed value. Right, so we want to figure out the probability. Let's see if you have to draw it out. 0.27. What is this probability here? What is the probability that our observation is, okay, what is the probability that our statistic would be beyond our observation? Observed. If this is very small, then it's very unlikely to have occurred, and so we can reject the null. Right, and this is kind of just the R code. And it turns out that it's 0.4. And normally we assume a 5% acceptance level. Since this is clearly bigger than 5%, that means you can't reject the null, right? That means your observation isn't too far off from your expectation, in a sense, right? And from this, we can draw a conclusion. We can't refute the initial assumption because it's not, the probability of it occurring isn't that bad per se, right? So you fail to reject the null hypothesis, and you must specify what the level was, right? Because the level you accept at would influence whether or not you accept or reject. right? And that's how you will do p-value hypothesis testing, right? So you need to figure out the distribution under the null, and then find the observed value, and then compare it to the relevant p-value. Now, the rejection region is another version, another way you can do the test. It's basically the same thing, but now instead of look at quantiles rather than percentiles, right? So you should get the same answer anyway, but it really just depends on which one you like more, really, or what the question asks for. The rejection region is just, if you imagine the 5% confidence interval of p-value thing, right? So two-sided test, we want the probability to be 2.5, 2.5, right? Rejection is really just the fact that, well, your observation is somewhere in this region, because if it's in that region, right, the probability that t is greater than your observed value is smaller than 5%. Right? Because if it's beyond, then there's less area to cover, and so the percent must be less than 5%. And hence you would reject it. Right? So they're pretty much the same thing, just looking at it from different perspectives. Quantiles rather than percentiles. And the way you'll set it up is basically this. So suppose, right? So the setting is basically the same alternate hypothesis. For here, this is known variance, right? Yeah, it's basically the same idea. Here you don't care whether or not it's positive or negative, so you just look at whether the observed value is too big in nature, in general, right? Here you're looking at whether or not the true mean is bigger than the assumed mean, so you would expect this value to be positive, right? And you will only reject it when it passes a certain threshold, which is this, right? Which is why it's greater than this positive value. And this thing is the reverse. You will expect to be negative. And so if it's extremely negative, so that's what this is defined as, extremely negative, you would reject it, again, because the same reason as the one above. Right? And t distribution, same thing. Just replace s, well, sigma of s, and use t n minus 1. The idea is basically the same as before. The only difference is that we need to consider a rejection region rather than p-value. Right? And you need to figure out the critical region. Right? Relevant rejection region. So if we look at the previous example, right? So this is the null hypothesis and this is the alternate. We know the null distribution is this thingamajiggy because there's only 4 observations. 4 observations. All normal and unknown variance, so we get T3. Unknown variance. 4 observations, T3. Right, so T4 minus 1. And from here, we reject it if the observed value, which is this, is beyond your critical value. Right, so in this context, the critical value would be, so this is a T distribution. This here, right here, is T3, 0.95. So this area over here, beyond, is 5%. Oh, what the heck? 5%. Right, this green region over here. Right, because if this thing lies within So if our observed value lies within that area, then the p-value would have been smaller than 5%, right? Because you have less error to work with. And so we just go through this, and we find the actual quantile. So this is quantile. You can use R, or you can use a given table, right? The given table, just look at the percentiles and figure out from there. And then we compare our observed value to this region value. Our observed value was actually this thing. So previous example, calculated. And clearly this does not lie in R because it's not bigger than 2.35336. Hence, we don't reject, or we fail to reject the null hypothesis under a 5% acceptance level. Right? So as you can see, it's the exact same conclusion, because really you're just doing the same thing, but from a different perspective. So the most important thing is to select the correct alternate hypothesis, rather than the method as to how you compare your rejection, right? P-value versus rejection region, doesn't really matter which one you go with, so long as you're doing it correctly. Right. Okay. Now you basically have this error term. The idea behind error is because, if you recall, hypothesis testing is proof by contradiction. Right? You assume the null and try to disprove it, or fail to disprove it, with uncertainty. Right? Since there's uncertainty, there's going to be some sort of error in your decision-making process involved, right? There's going to be some level of error involved there, right? And these are the two types of errors, type 1 and type 2. Obviously, they're bad because, well, the word error is a bad thing. And we know, and if you just read it, so assuming that the null hypothesis is true, but you reject it, that's bad, right? And the reverse is also bad. The null is false, but you fail to, or you accepted it, or you failed to reject it, right? That's obviously not good either, because you want to be correct. Right. And now, the alpha level, so like the alpha equals 0.05, this is actually your type 1 error. So by shrinking the alpha, you control the type 1 error, essentially. The reason why is basically because, if you recall the rejection region, it's all based on the fact that the null is true, right? Because the p-values and stuff was all based like, okay, assuming the null is true, we have this p-value, we have this distribution, right? And we reject it, right? And since we made the range 5% arbitrarily, that as a result means that 5% of the time we run this test, because the distribution could be like any of those values, it's going to be rejected, right? And that's why the type 1 error is the alpha level. Right, so we'll go over this last thing here. I won't go over likelihood ratio test because that's minor apparently in this course. So we'll go over asymptotic test, the Wald test. The idea is basically, well, if you have an estimator that's asymptotically normal, right, and you want to test this statistic or hypothesis, really, then all you do is kind of use standardized normal. This is just standardized. It's normal, in a sense, right? Kind of looks like a normal standardized. You just minus the parameter and divide by its standard deviation. Right, and the way you would do the test is, well, since it's two-sided, as you can see here, you just use the two-sided test for normality. Right, you could do the same thing for one-sided test, because again, you just use the fact that it's asymptotically normal. So you just pretend that this thing's normal, so the whole entire setting is pretty much the same anyway. Right, so here's an example. So we're going to consider the example of the MLE, so the log normal. Oops, that's not what I meant to write. Log normal. 0 sigma squared distribution from before, from the MLE. Suppose this is the actual estimate you found, and it's based on 20 observations. We want to now test our hypothesis that this is actually the true value of sigma versus the fact that it's not 0.5. Right? So the way you'll set it up, really, is the fact that you use the volt test, because you know that sigma MLEs are asymptotically normal. Right? So you just kind of plug into the volt test. Right? So you put in the MLE minus its true value, so the assumed true value here, this thing, and you divide it by its standard error or standard deviation. So you standardize it essentially, and you just sub everything now. So the standard error of an MLE is the what's this called? Inverse square root. Okay, whoops. Okay, so this figure up here was found to be, we found this through the Fisher information. And we inverted it, then we square rooted it and everything like that. It's from earlier in the slides. Right? So now all you do is sub everything in. Right, as you can see, 2 times 20 over here. This thing here. So that's your sigma thing. And here's just sigma element. So this thing. Right, and under the null, it's normal 0, 1, because essentially the process standardizes it. Right, that's what we did earlier. And all you do now is sub in MLE. Because everything, this whole thing just depends on MLE now. Sigma MLE. This thing here. So just sub in to W. You sub that all into W, you'll get a value, and it turns out to be 1.97515. Right, so it'll be something like square root 40, 0.72706 minus 0.5, oops, over 0.72706. Right, so go through this, and then now I'm going to do the rejection region, because I prefer that one, because you can just look at the table really. And we need to look at the critical values, because we know it's asymptotically normal, for a standard normal. This is a two-sided test. Because we're testing the fact that it's not 0.5. So you don't care if it's negative or positive. You just say like, okay, it's not 0.5. Right? You don't care if it's bigger or smaller. Right? So you look at the region where it's 2.5% above, 2.5% below. So if you were to draw out the distribution, here, 2.5%, 2.5%, right? And since it's symmetric, right? These two values, 5, Z 0.975, they're negative of each other, right? So just minus of each other. That's why we just consider the absolute of this big one. And you can see that the observed value, which is this, so the value you subbed in your information into, is actually bigger than the critical region. So that means it's in the critical region. That means your observation is very unlikely to have occurred based on your initial assumption. So we can reject the null hypothesis. And so you can conclude that the true standard deviation isn't 0.5. Right, so you can see how it's a proof by contradiction, right? You assume something and you see how likely it is based on that assumption. And we have the likelihood ratio test. I'm not going to go over this because it's not really as important. Alright, doesn't seem to be as important. but you can go through it in your own time. Right, so thank you guys for coming. Sorry for going over time, right? Like 10 minutes, that's my bad. But yeah, good luck on your finals. And if you have any questions, feel free to ask me like now if you want. Right, and I can re-explain some parts earlier. If not, then yeah, that's pretty much it. So good luck to everyone on your finals. So we just went through the whole statistical inference part here. Alright. Right. Oh, I guess I should mention, this is more important in future courses, the likelihood ratio test. Because you can test multiple parameters at once. Alright, doesn't seem like anyone has any questions. So I'll just... Yeah, I guess I'll give a quick recap, huh? Okay, let me go to the very beginning. Okay, let me go to, for some reason. Let me go to the very beginning, so I can highlight what we went through again. Whoops, it's not loading. But yeah, this part of the course was basically the second half. Right, so the most important thing is hypothesis testing and knowing how to estimate random variables. Confidence intervals is kind of related to hypothesis testing. I didn't really mention it in this seminar, but that's why you can pretty much kind of see the relationship in confidence and hypothesis testing for the normal distribution. Right, it's more obvious there. Yeah, it should be fine. Right, I'll just end it here then. So thank you guys for coming. Right, okay, let's see. Boom, boom, boom.